In 1929, Edwin Hubble made a remarkable discovery. Galaxies far from Earth were moving away, at increasingly faster speeds. It meant the universe itself was expanding. Roughly 70 years later came an even more remarkable discovery. Supernovae were moving away, much faster than scientists had expected. The expansion of the universe was accelerating. This was something the existing laws of physics couldn't explain. To explain it, scientists proposed the idea of an invisible force, speeding up the expansion, what we now call dark energy. Dark energy is estimated to make up about 70% of the entire universe. The problem is we've never directly observed it. We can only infer its existence from phenomena that can't be explained without it. Still, dark energy has helped explain a wide range of astronomical observations, from the structure of the universe to the cosmic microwave background. That's why we have continued to believe that dark energy must exist. But science is a discipline that constantly tests old theories against new discoveries. And in 2007, Professor David Wiltshire and his team from the University of Canterbury proposed a radically different interpretation. They suggested that the so-called accelerating expansion of the universe might be an illusion, and that dark energy might not exist at all, according to a theory called the Timescape model. Before we dive into this model, we first need to understand the existing one. To explain the accelerating expansion, scientists introduced dark energy and proposed a standard cosmological model that includes a cosmological constant, lambda, along with cold dark matter, the so-called lambda CDM model. This model is built on two key assumptions. 1, gravity in the universe follows the rules of general relativity. And 2, matter is distributed homogeneously throughout the universe, and the universe appears isotropic in every direction. With these two assumptions, scientists could simplify the vast universe into a single homogeneous entity. This made it easier to describe its expansion mathematically. General relativity is a physical law repeatedly confirmed through countless experiments and observations, but the assumption of large-scale homogeneity is now being challenged. Recent discoveries of massive cosmic structures, like superclusters and vast voids, suggest that the universe may not be perfectly homogeneous after all. Moreover, discrepancies in the Hubble constant, the so-called Hubble tension, have raised further doubts about the lambda CDM model itself. When we look at the cosmic microwave background, the universe appears extremely uniform on a macroscopic scale, or to be more precise, it had been uniform. That's because when we observe distant parts of the universe, we're actually seeing it as it was in the distant past. The early universe was indeed highly homogeneous, but when we observe regions closer to us, representing more recent times, we see that homogeneity gradually breaks down. Over time, matter began clustering around regions with stronger gravity, while other regions were left empty, forming what we call voids. As a result, the universe evolved into the web-like structure we observe today. The Timescape model argues that within these vast cosmic structures, we must account for something often overlooked: how gravity affects the passage of time. Time doesn't pass at the same rate everywhere. According to Einstein's general theory of relativity, time slows down in regions with stronger gravity and speeds up where gravity is weaker. One scene from the movie Interstellar captured this idea beautifully. When the crew landed on a planet with intense gravity, only a few hours passed for them, but decades went by for the colleague waiting on the spaceship. The same principle applies here. In this cosmic web, time would pass more slowly in dense, gravitationally rich regions, while passing faster in the vast, empty voids. So even if the universe expands at a uniform rate, differences in the passage of time could make that expansion appear different, depending on where we observe it. If we ignore these variations in time and assume the universe is perfectly homogeneous, we might mismeasure its expansion, creating the illusion of acceleration. And if that's the case, one of the biggest mysteries in science, dark energy might not actually exist, or may never have been needed in the first place. This is the central idea of the Timescape model. Using the Pantheon plus supernova dataset, the research team compared the Timescape and lambda CDM models. After analyzing around 1,500 supernovae, they found little difference between the two models for distant objects. But for closer supernovae, the Timescape model fit the data slightly better. Of course, supernova data alone is not enough to fully replace the lambda CDM model. Lambda CDM still explains the large-scale structure and the cosmic microwave background more effectively, something the Timescape model has yet to fully achieve. But one thing is certain: there is still something we're missing, something we don't yet understand. Once again, we stand at a crossroads. What matters is that we never stop asking questions, because the more we explore the universe from new perspectives, the more it reveals its secrets in return.